So, the two pictures I have up on the smartboard are hopefully familiar to you from chemistry. I have solubility curves on the left, and I have our double displacement, which things were soluble versus insoluble, on the right. In particular, the thing on the right, our solubility table, is a simplification we gave you in Chem 1. That it's not as simple as is this soluble or not, because quite frankly, anything that's ionic should be able to dissolve a little bit in water. Now, things have more attraction, so they create precipitate, sure. But a little bit of a simplification here. Between both of these things that reference solubility, we have to include equilibrium within it. And that's kind of what today is going to be about. I don't know if you need to write this down. This is just me reminding you of a couple things. So again, solubility table simplification. If you remember K values, a large K value, as we are going to get into what's called solubility product today, which is KSP. A large K value would represent that that ionic compound does dissolve really well. Sodium chloride would have a huge K value, so would potassium nitrate. So if that's the case, they are soluble. We're going to be working with things that have tiny K values. Things that on the solubility table we would say is insoluble, but they can be a little bit dissolved. We're going to figure out how much of those things could be dissolved. Do I even have another thing on the slide? Oh, I do. Okay, again, I don't think you have to write down this last bullet point. I mean, if you want to jot anything down this page, large K values mean soluble would be the thing to know. I think even the goal sheet that you picked up today with solubility product talked about if the K value is at least a value of 1 or larger, we consider it to be pretty soluble in water. All right. So, what solubility product is referring to is if I put a solid substance in water, how much of it would dissolve? Now remember, at any given moment, if it's not going to completely dissolve, some of the solid could dissolve, but then some of the aqueous would undissolve. It would be an equilibrium response. It's not like it just stops. That, okay, we've dissolved as much as we can. Now, if you haven't dissolved, you never will. It's not how it works. So that's why I kind of mentioned there's going to be this back and forth, dissolve, undissolve. Well, that's what equilibrium is. This would be the expression for that. So if we had solid silver chloride, it would break down to silver ion and chloride ion. If I were to solve for the K of that, it'd be the concentration of Ag times the concentration of Cl. Notice that I did not divide it by a reactant AgCl because it's a solid. K values are based upon things that can change concentration. Pure solids and pure liquids do not have a concentration. So it has to be only based upon the aqueous things.
I'm looking for evidence.
Isn't there? So you go through that.
Alright, sorry guys.
Now when Caitlin listens to notes, she can hear Miss Lancer looking for heaven. No longer so. Back to the chills. You ready? Okay, I'll give you a second example. Okay, this example, notice that there's 2 chlorides in this one. So as a quick reminder, we would have to square that value. So again, we should hopefully be comfortable with this. We are making assumptions, however, that we don't have any of these ions pair up at all. I don't think that should be an issue. Actually, I'm going to get rid of that assumption part. Okay. So that was kind of the brief intro to start off with. We're basically showing a dissolving equation, but realizing that it won't all dissolve. We think back to the solubility chart that I showed you with all the curves. In Chem 1, we talked about how if you're on the line, you are saturated. If you're below the line, you're unsaturated. If you're above the line, you're supersaturated. Well, actually, we can numerically solve for that with K values as well. Because remember, reaction quotient is any other time other than at equilibrium. So if I were given initial ion concentrations in solution, I could mathematically solve for is it saturated or not. Because if I did my K math for that, and my reaction quotient value was less than K, that means I could still have more ions dissolve. I could get that number bigger, it would be unsaturated. If, however, it equaled, it would be saturated. And if it was greater than K, it would somehow be supersaturated. Now, besides saturation, what I wrote on there is whether or not it could create a precipitate. Because what we're going to focus on a little bit more next class period is what happens if I try to do a double displacement reaction. Again, too often we rely on that solubility table with the insoluble-soluble markings, but really K values is what's going to tell us whether or not a precipitate is created. And we're not going to get into that level today. We're going to start off with just the dissolving part today. So what I'm going to show you is kind of a path mathematically that we will take in order to figure out these problems. I don't know if you necessarily want to write down the path that I show you, or if you will more just the two practice problems that I show you, you'll go over that instead. So I actually stole this from an old textbook where there's one of two ways that you could do a problem like this. You could be either given the K value for the compound, and you have to go right to left on this chart of these blue squares to solve for the solubility, so how much is dissolved in water. Or I could tell you how much is dissolved in water, and you could solve for the K value. So I'm going to do one practice problem of each direction to kind of wrap up notes, and then you would be able to do the sheet you picked up on the way, and that was titled Solubility, Equilibria, Practice Problems. And then whatever else we need to work on as well. And there's already a web assigned over for that too, so you could do that as well. The one thing I did note for my 2 bullet points, typically I've seen more questions ask for molar solubility, so in other words, what's the concentration of each ion at equilibrium or when it's dissolved. However, we could just go to regular solubility as well. Regular solubility isn't your moles per liter, it's your grams per liter. So how much mass of solute would be in that solution as opposed to moles of solute per solution. Okay, so again, I don't think you have to write down this. I'm going to switch over to Smart Notebook and show you the problem, but we could give you something as simple as calcium sulfate have 0.67 grams per liter dissolved in it. With that information, you could solve for the K value. Kind of like if you're given the equilibrium concentrations of things, you could then solve for the K value from what we've done in the past. I'm just kind of breaking down the steps that I would do in order to figure that out. So the first thing I like to do with this, 0.67 grams per 1 liter, and that was of calcium sulfate. Convert your grams into moles. That's what we always do. So again, 0.67 grams per liter is what we would just call your solubility level. 0.00492 molar is your molar solubility. It's the concentration of these ions. Now, if I were to write out this equilibrium expression, again, remember these two things are aqueous. This is a solid, which is why it's not going to have a concentration. If I started off this process, before dissolving would begin, I'd start with 0 of each of these things. Some textbooks, instead of using X as your variable for change, like to use S for this type of problem because it's solubility. So if you looked at your textbook, don't be thrown off by that. But in essence, I don't even know if an ice table is that necessary to know that at equilibrium, it would be equal amounts of this and that because they're in a 1-to-1 ratio. So remember when I showed you K before, K would equal the concentration of the products. X times X, which I'm just writing as X squared. What is the concentration of each thing when that comes along? It's that guy right there. That's our X value. So if I give you either the solubility or the molar solubility, that is the value for whatever has a 1 coefficient in front of it in this equation. Which means if I wanted to solve for my KSP, it'd be 0.00492 times 0.00492. So this particular problem, now I'll go down to 2 sig digs because 0.67 had 2. 2.4 times 10 to the negative 5th would be my K value for this first problem. And I don't even know if the ice table is necessarily needed for this type of problem, especially when it's a 1-to-1 ratio. But that's all I wanted to remind you of with that part there. So one more time before I switch over to the next problem. If you're given either solubility, which is your grams per liter, you could just do a mole conversion to get to what we call molar solubility. That molar solubility then is in essence our X value. So now what we can do is plug that in to solve for K because, again, products over reactants, but the reactant is a sol, so it is just products that we're looking at there. The other version I could give you would be you're given a K value, and we want to find either the molar solubility or even the grams per liter, which would be just solubility. So I'll show you this one on the smartboard now as well, copper 2 hydroxide. Notice that, again, there's a 2 there. So if I kind of abbreviate my ice table a little bit and just at equilibrium. This would be an x and a 2x, right? Again, textbooks might call it S for solubility instead. I don't know, x is the variable. If I wanted to solve for K, remember, products over reactants, except for we're not going to consider this reactant because this reactant is a solid. So it'd be x times 2x, right? Oh, I have to square it, right? There. So, K value was given to us in this problem. That was 2.2 times 10 to the negative 20th. Let's look back here. 2.2 times 10 to the negative 20th. This would equal 4x cubed. Divide by 4, take the cube root. This would give you an x value of 1.8 times 10 to the negative 7th. This is a molarity. This is your molar solubility. Because remember, whenever you have an equilibrium ice table, unless it's a Kp for pressure, you are solving for concentration when you solve for x. So my concentration of copper ion would be this value. My concentration of hydroxide would be twice as much that value because it's a 2x. If I wanted to stop there at molar solubility, this would be my answer. If I wanted to get into just solubility, that is where sometimes it's easier visual to realize that this is moles per 1 liter. And now I need to cancel out the moles and get to grams for that copper 2 hydroxide, which there's 97.57 grams in 1 mole of copper 2 hydroxide. So the solubility of copper 2 hydroxide would be 1.8 times 10 to the negative 5th liters per mole. I'm sorry, grams per 1 liter. There's a reason why the solubility table would say that this is insoluble. Is because that is a tiny amount of grams for 1 liter of water. So since that's the most that you could dissolve, it's basically like saying that it's insoluble, because any normal amount of solid in water would not have it dissolve to much extent at all. So this is kind of why that solubility table we gave you in Chem 1 is a simplification, because this isn't very solid. Some things are a little bit more than this value, but in general, we're looking at those things that are considered insoluble. We just have to recognize that they're not completely insoluble.